This is one of a series of 6 general revision videos for higher tier maths GCSE. These are based on the revision mats available from pixiemaths.co.uk for free that cover the 6 different branches of the maths GCSE. So I'm just going to go through them, answering the questions in the way that make most sense to me. I'm not going to be reteaching topics, but just explaining what I'm doing, hopefully as a reminder for how these various skills work. So I'll start off with the applied ratio questions in this box here. The drink is mixed in the ratio lemonade, orange to cranberry, 6 to 3 to 2. What fraction is orange? So we've always got the same order of things, so orange is in the middle. It's 3 out of a total of 10 parts, 11 parts, sorry, 6, 7, 8, 9, 10, 11. So we've got the total share is 11, and we're talking 3 out of 11 is the fraction that is orange. Question 2. Washing powder is sold in 2 sizes, 600 grams and 1,500 grams. Which size is better for value for money? Lots of different ways of doing this. You might work out how much you can get for a pound. We've also got a 15% off to consider. So, yep, let's do it that way. How much you'd get for a pound? That would be 600 over £3.30. Which is 181 grams for a pound, 181.8 grams for a pound. This one is 15% off, so I need to do £9.60. Quick way of taking 15% off is to times by 0.85. Which gives me £8.16. So if I want to find out how many grams per pound I get, I do 1,500 divided by £8.16, which is 183.8 grams for 1 pound, which is more grams for a pound than this one. So the green box is better value for money, just. Normally in an exam they'd have them box labelled A and B, so B is better value. Another way to do that, I'll just go through because a lot of people might have done £3.30 divided by 600. That's going to work out your cost per gram, which is just as valid a way as the other to work out. And some people might think this makes more sense. Apart from the values we get are very small. So that's 0.005 pounds per gram, or I would say you could do gram per kilogram and things as well. There are loads of different ways of comparing. As opposed to get sensible numbers, I could do 330 divided by 600. So let's try that. That gives some sensible numbers to compare. All of these work. I'm just thinking of the best, clearest method to demonstrate. That's 0.55 pence per gram, and if I was to do the same with this one, I'd have 816 pence over 1,500 grams, which is 0.544 pence per gram. So any of those ways, and there are plenty more besides as well, just to compare those two values. But either way, it turns out that this one is cheaper, B is cheaper. Question 3. Laura buys a saddle in the UK for £850. Delivery is free. Steve buys the same saddle from Holland for €990. He pays €15 for delivery, and £1 is 1.18 euros. Including the delivery charge, whose saddle is cheaper? So we want to split up our working into Laura, which is just £850 and delivery is free. So I want to either convert that into euros to compare to Steve, or do the other way around. I'm actually just going to compare this into euros. So I get more euros than pounds. So I'm going to multiply 1.18 And just check that I've ended up with what I expect. More euros than pounds. Sorry, that should not have a pound sign, it should have a euro sign. So Laura's cost 1,003 euros. Steve cost 990 plus the 15 euros delivery. So that is 1,005 euros. I put equals 1,005 euros. Whose saddle is cheaper? We would write 1,005 is greater than 1,003. So Laura's is cheaper. Question 4. Here are the ingredients to make 8 biscuits. Work out the ingredients to make 20 biscuits. So we need a scale factor here. I need to get from 8 to 20. What do I do to get from 8 to 20? Well, you can think of it as either 20 divided by 8 to find that scale factor, which is 2.5. That's the scale factor. Another way to think of it in practical terms in a kitchen, if I wanted to get from 8 people to 20 people, I would double it and add another half. So that is doubling and adding another half is the same as multiplying by 2.5. So I'm going to multiply each of these by 2.5. So it needs to be done in turn. I've got 187.5 grams of flour. I've got 125 grams of sugar. ,100 grams of butter. And this doesn't quite work, this recipe, because I'd have, oh yes it does, 5 egg yolks. Of course it does, yep. Another doubling it and adding one more, 5 egg yolks. So all of those needed for the 20 biscuits. Okay, this is where ratio and proportion overlaps with algebra. I've got direct and inverse proportion. So y is directly proportional to r squared. That leads me to this statement. Y is proportional to r squared, which means that y equals some value k times by r squared, some unknown number times by r squared. When r is 4, y equals 24, so I substitute into this formula 24 equals some number times by 4 squared. So 24 equals 16k, and k equals 24 divided by 16, which is 1.5. Go back to my original formula, y equals, but now I know what k is because I've worked it out, 1.5 r squared. Work out the value of r when y equals 1,350. So if y is 1,350, 1,350 equals 1.5 r squared using that value of k that I found, which is the link between the two values. So r squared is 1,350 divided by 1.5, which is 900. So r is the square root of 900, which is 30. Similar idea here, but inversely proportional. Inversely proportional means that y is proportional to 1 over x squared from the question. Inversely proportional to x squared means I've got that as my starting point. We're told that x is bigger than 0. That means that y is equal to some value divided by x squared, and we've got again our link pairs to start off with. They're always quite formulaic, these questions. 20 equals k over 2 squared. To get k on its own, I multiply by the denominator, so 2 squared is 4, 80 equals k, and I go back to my original formula, therefore y equals 80 over x squared. And I'm asked to find the value of x when y is 5, so I've got 5 equals 80 over x squared. That means that x squared, I can switch places there, 80 divided by 5 is 16, and therefore x is root 16, x equals 4. Could have been minus 4, but we are told that x is greater than 0, so the only answer that is relevant here is x equals 4. In this one, w is directly proportional to y, so no squareds in there. This is a more straightforward one. Proportional to y, that means w equals k times y. When y is 4, w is 14. Same idea here. Substitute in 14 for w, k times 4, 4k. Divide both sides by 4, and I get 3.5 equals k. So go back to my original formula, w equals 3.5 times k. 3.5 times y, sorry, 3.5 times y. I'm told that y is 9, w equals 3.5 times by 9, so the value of w at that point is 31.5. Similar one to here, w is inversely proportional to x squared, proportional to 1 over x squared. That's what inversely proportional means. When that means w equals k over x squared. K is some number. So substituting in w, 5 equals some number over 2 squared. That number, multiply both sides by the denominator, that's 4 times 5. 20 is k, which means my formula is w is the 20 I just worked out over x squared, using that formula. Work out the value of w when x equals 10. So w equals 20 over 10 squared, 20 over 100. W equals 0.2. Okay, next topic is recurring decimals. Which one of these, when converted to decimals, are recurring decimals? So 1/3 we know as 0.3 recurring, so that one is a recurring decimal. Pi is an irrational number, which means that there is no recurring going on. We know it's 3.142, etc., and it carries on with decimals forever and ever that don't repeat, and the same is true with root 3. So neither of these are recurring. They're what we call irrational numbers, both of them. They can't be written as a fraction, and they don't recur. 3 over 16 is 0.1875, which is not a recurring decimal, so I don't ring that one either. And 5 over 7 is recurring. The pattern here is quite confusing. As always, when the denominator is 7, it does recur, but it recurs over quite a long time period. We've got 714285, and then it recurs again, 714285, 714285. So 5/7 is also recurring. In general, what we're looking for is denominators that involve a 7 or a 3 or an 11 perhaps, a 9, any multiples of those. If the denominator only involves multiples of 2 or 5, then it won't recur. But of course, you can try it out on your calculator or longhand if you need to. Show that 4/9 is equivalent to 0.4 recurring. I think the best thing to do here would be to do 9 going into 4, which is what 4/9 is. 9 goes into 4 0 times with a remainder of 4. 9 goes into 40, well, 4 9s are 36. So it goes into 40 4 times with a remainder of 4. 9 goes into 40 4 times with a remainder of 4. And this pattern will keep repeating and keep repeating. So that's probably the easiest way to show that 0.4 recurring is equal to 4/9. Using part A or otherwise, write 0.94 recurring as a fraction. Well, I'm just going to use this, I could use part A, but I'm going to start it from scratch because this is a standard topic of turning a recurring decimal into a fraction. So I'm going to first of all define x as the recurring decimal, and I'm trying to scale it up so that I'm going to multiply by 10 or 100 so that I end up with just a string of 4's in the right place. So I'm going to use 10x equals 9.444, etc. I'm going to subtract the top one from the bottom one. That's a bit confusing, the other way around to normal. Perhaps let me write it like this. If I subtract this line from that line, that leaves me with 9x on this side, 10x minus x. And on this side I've got 9 minus 0, which is 9. Oh no, I should have done, whoops. 9 from 4 doesn't work, so I have to borrow from that. 9 from 14 is 5. And 0 from 8 is just 8, so that's 8.5, and then all of the other 4's will cancel each other out. That's why I've written it like that. So I've cancelled all of those. 9 from 14 is 5, and 0 from 8 is 8. So 9x equals 8.5. Therefore x equals 8.5 over 9, but of course I don't want to leave a fraction like that with a decimal in it, so I will I can either times by 10 or just double top and bottom, because doubling it in this case will lead to a whole number. So that is 17 over 18. Same idea here, converting 0.172 recurring to a fraction in its lowest terms. So I've got x equals 0.1727272. Because I've got two recurring digits here, I can't just shift everything up by 1 like I did before. I've got to shift it up by 2 spaces, so that's 100x equals 17.272727. And I'm going to write that out underneath. X equals 0. Lining up the decimal places, 172727, etc. All of these bits will cancel each other out when I subtract. 7 from 7 is 0, 1 from 2 is 1, and 17.1 on this side. 100x minus 1x is 99x equals 17.1. And that means that x equals 17.1 over 99. Of course, that's not in its simplest term, so I'm going to times top and bottom by 10. X equals 171 over 190. I'll do a quick check to, 990. Quick check to see if 3 will go into that, because I can see it can go into the denominator. Top digits add to 7, 8, 9, so 3 will go into that. 3 goes into 17. This would be non-calculated, by the way, that's why I'm doing this longhand. 3 would go into 17 5 times with a remainder of 2. 21, 3 goes in 7 times. 57 over 330. Is this divisible by 3? Yes, it is, so I can divide by 3 again. So that equals 3 goes into 5 once with a remainder of 2. 3 goes into 27 9 times. 3 goes into that 110 times. I think that's my final answer. Yes, must be, because 19 is prime. So my final answer is 19 over 110. Okay, reverse percentages. Work out the price of the car before it was reduced, and we've got 25% off is now 14,625. So if I'm taking 25% off something, I am multiplying that by 0.75. That's a reduction of 25%. So if I need to go back to what it was beforehand, I need to take my output number, what I've ended up with, and divide it by 0.75 to go back to what I started with. Whenever we're working backwards with percentages, we are going to be dividing. If you're working forwards, you are always multiplying, even if you're multiplying by a number less than 1. So that started off at £19,500. Obviously, in an exam, I would check that. 19,500 take away the 25%, gives you 14,625, so we've got the right answer there. Question 2, I increase a number by 24%, the answer is 6,014. What number did I start with? So to increase by 24%, that would be multiplying by 1.24. Same technique, I'm working backwards, so I've ended up with 6,014, and I need to divide by 1.24 to get back to my original number, which is 4,850, dividing by that multiplier. Question 3, in a sale, the normal price of a dress is reduced by 25%. The sale price is then reduced by £10. The dress is now priced at £80. The manager says the price is now 1/3 less than the normal price. Show that he is correct. So, less than one is now 1/3 less than the normal price. So let's see what's happened here. We've taken our X value, and the dress is now priced at £80. So let's see what it was originally. We've got £80 plus the £10. And then we're going to undo this reduction of 25%. So I'm going to divide by 0.75. Gives me 120. That's the original price. For the original price is 120. 1/3 by 1/3, reduce 120 by 1/3 is 120 minus 40, that's a third. It's £80, and therefore it's correct. You would want a lot more space for showing you're working on an actual exam paper, and try and structure your working so that it's clear what you're doing in each case, because it's a show that question, which means it needs to be clear. Jane and Laura each have a meal. Jane pays £41.80, which includes a £4 tip. Laura also pays £41.80, which includes a 10% tip. Who pays the greater tip? So we're seeing, is that including a 10% tip? Is that 10% tip greater than £4? Because we're looking for the greater tip, not the greater bill. So if that includes a 10% tip, that is 110% out of the original bill. So if I want to find out what that 10% is, I could take that £41.80 and divide it by 1.1 to find out what the original bill was. That's 1.1 from there. £41.80 divided by 1.1 gives me £38 as the original bill. £41.80 minus £38 is £3.80, which is obviously smaller than £4. So £3.80 is less than £4. So Jane has the greater tip. Jane pays the greater tip. Two boxes left to do. Exponential growth and decay. The population of Knappsford in 2010 was 3,800 and is believed to be growing at a rate of 1.5% a year. Calculate the population of Knappsford in 2011 and 2012. So take that population, multiply it by 1.015 is 1.5%. 1.5% increase, I should say. So that is 3857 in 2011. And in 2012, take that number from 2011 and do the same thing to it. Increase it by 15%. that is 3914.855. So I'll call that 3915 as the population. Question 2. The population of a form of algae is believed to grow exponentially. On day 1, the population of algae was 2,240. By day 4, it increased to 35,000. Calculate the population of the algae by day 10. So, believed to grow exponentially, that means that we've taken our 2,240 and I've multiplied it by some number, which I'll call k, and I've multiplied it 3 times by that number k, by that percentage multiplier, whatever it is, 1 point something, to get to 35,000. And I just want to check with my counting. Day 1, it was already 2,240, so I've multiplied it once to get to day 2, second time to get to day 3, third time to get to day 4, and that's why I've got that number 3 there. Always worth counting to make sure you've got that starting point right. So I need to find out what this multiplier is. So k cubed is 35,000 divided by, whoops, not multiplied, divided by 2,240. Which is 15.625. K is therefore the cube root of that. Which is 2.5. Oh, so it's growing by 1.5% each day. I then need to work out the population of the algae by day 10, so that is 9 days after the original. So I'm going to do 2,240 times by 2.5 to the power of 9. Which is, that's day 10. Times 2.5 to the power of 9, 854,000, nope, 8,544,921.875. So I'm just going to call that 8,544,922, rounded in the normal way. Okay, final box in this document, compound interest. So Lauren put £600 in a bank account. The account pays 3% compound interest. That is 1.03 as a multiplier. 1.3 would represent 30% compound interest, and we've always got to be aware of that. So 1.03. After 1 year she withdraws £200. How much will she have in the account after 2 years? So we've got 1 year. At the end of 1 year, she has £618, including the interest that she's earned. But then she takes out £200, so she's left with £418. But then she gets another year's interest on that £418. How much has she got on the account? It's that 418 times by 1.03. Which is £430.54. And I would put all of those digits in because it's money, so I would do pounds and pence. £430.54. Question 2. An amount of money was invested for 8 years. It earned compound interest at 2.5% per year. That is a multiplier of 1.025, not 1.25. After 8 years, the total value of the investment was this. Tom is trying to work out the total interest earned. State what is wrong with Tom's method. So the problem is he has multiplied his starting value by a quarter, less than a quarter, by that He's tried to find the 2.5% interest, and he's multiplied it by 8. What's wrong with Tom's method? Firstly, he needs to divide by 1.025, and instead of multiplying by 8, so it should be divide by 1.025 instead of multiply 0.025. And he should also be, 8 should be a power, not a multiplier. So if we're going to work out how much it actually is, which is not what it says here, but I would take that value and divide by 1.025 to the power of 8, and that's going to tell me how much he had in the account at the beginning. We're trying to work out the total interest earned, so we're going to compare what I get from the beginning with this value at the end. So 11696.67 divided by 1.025 to the power of 8 gives me £9,600. There are some few trailing decimals there, but it's basically £9,600. And therefore interest earned is 11696.67 minus that 9,600, which is £2,096, 67 interest. It didn't actually ask us for the value of interest earned, but we can see that this method, 8 should be the power, and it should be divided by that instead of multiplied by that. And even if it had been, it still wasn't quite the right answer. If you tried doing the calculation on the post-it note, you'll find we get a very different answer. £2,339. Not totally different, but different enough. Okay, final question. John bought a 2-year-old car for £12,000. 3 years later he decides to sell the car. I think the value of the car is inversely proportional to its age. John estimates the value of the car using this idea. The actual value of the car depreciates by 20% each year. Work out the difference between John's estimate and the actual value. So John thinks that the value, V, let's call it, is inversely proportional to its age. So the link value we've got here is that its value was £12,000, and that equals some value over the age, which is 2, and therefore K is 12,000 times 2 is 24,000, which would give it a value when new, value of 24,000 over 1, we've got 24,000 over A, value when new of £24,000. 3 years later he decides to sell the car. So 3 years after that is, he thinks John's estimate would be 24,000 over that 5 years. Which is £4,800. But actually, the car depreciates by 20% each year, so the actual value is, it's 3 years after that, 12,000, doesn't matter about the initial value because we're just going from what it cost 2 years in, and it is decreasing, therefore we've got by 20%, so that's multiplied 0.8 for 3 more years, 12,000 times by 0.8 cubed is £6,144. Difference is 6,144 minus 4,800, which is £1,344. Okay, that's the end of that one. I think all questions answered. Yep, so the other topics are listed in the other 5 videos that go with this one, and that's basically all the key skills needed for higher tier GCSE. But of course the real challenge of the higher tier GCSE is where these high level questions get put together in different contexts so that you are problem solving with these skills. Good luck!